So we'll see how we do here. What we're going to try to do is give you an overview for how you go about doing some basic exploit research, discover a vulnerability, discover what you need to know in order to turn that into a proof of concept for an exploit. And then we're going to go one step further. It didn't mention it in the outline there, but we're going to show you how to convert that into something you can use with Metasploit. Because Metasploit is an extremely popular tool. It's easy to use, fairly easy to use. The one thing that's a little bit lacking is that the API, as good as it is not extremely well documented. What I mean especially is that if you want to take an exploit and turn it into something you can use in Metasploit, there's really no document to say, OK, you do this, then this, then this, then this. You just have to kind of figure out the secret sauce. So we're going to show you how easy that turns out to be. To get started here, let's, I feel like I'm awfully loud. Could you guys turn me down a little? Because I'm even loud for me. All right. So we're going to work through this here. I'm going to flip back and forth between slides and actually developing an exploit. We're going to first talk a little bit about how buffer overflow exploits happen. There's two main kinds that you run into. Buffer overflows, all of them, deal with a very simple concept. It's right here. Overflows is you've got too much stuff and you're trying to put it into too small a space. A friend of mine, he's a carpenter. His wife loves shoes, so he built her this beautiful set of pigeonholes. Remember pigeonholes for putting your mail in? He built her pigeonholes for her shoes. It has 64 slots. What happens when she's got 65 pairs of shoes? They don't fit anymore. It's an overflow. And it's really as simple as that. We've got some piece of memory that's been allocated to store stuff, and we try to put more stuff than we've got space for in the memory. What effect does that have? It turns out that in a lot of the code that we run, there's very little checking to see if we've gone too far. It just assumes that if we've put stuff there, we must know what we're doing, and it's not going to question us. So if I were to allocate some memory and then put some stuff in it and put in too much stuff, what's going to be happening? What am I doing when I go past the end there? What do you think? Feel free, you can shout out here. I'm going to hit, I must be overwriting something important in there. Maybe it's another variable, or I don't know, but it's going to overwrite something. It can't be good. There are two main types of overflows that happen in our code today. We have stack overflows, and we're going to talk about stack overflows tonight because in some ways they're much easier to demonstrate, and it's a good starting point if you've never really, you've heard about them, you've never seen how one works. This is a good starting point. They're easy to understand. The other kind is a heap overflow. They're really not any different. It's too much stuff in too small a space. We're overflowing a variable. It's just where in memory it happens. The stack is a temporary space that it maintains as programs are running and uses to transfer information back and forth between subroutines. The heap is the dynamic memory. It's where global variables will be stored, things like that. We need to allocate additional memory. It's all going to come out of the heap. So that tends to be toward the lower part of the memory in a program. We're not going to focus on those. We'll just deal with the stack overflow. And to deal with that, we're going to look at where the stack overflows tend to happen. And this is why they're easier to deal with, by the way. They tend to, the stack is always used when we're passing arguments into a function. So within our code, if it's going to call some subroutine, it will always be putting the arguments on the stack. For our purposes tonight, it's not a programming class. We honestly don't care what order it puts them in. We really don't care where exactly on the stack they are. It just matters that they're going on the stack. So when the subroutine runs, it knows to find them there. It knows where to look. You'll also find that any locally defined buffers or variables in a function, in a subroutine, will also be defined on the stack. It'll actually just allocate some RAM and tell the function, hey, here's where your stuff goes. And the function will take care of putting things where they belong. The reason that this stuff is important, though, is there's another very important region on the stack. Every time a function is called on the stack, the parameters, as the function is being called, on any arguments, are pushed onto the stack one at a time. And then right before the program enters the subroutine, before control is transferred, it's going to push two additional things. It's going to push a stored frame pointer, which for our purposes means where was the stack before? Where were we before the function got called? And the other thing it pushes that's extremely important is where was the code executing before? Because we're running along and then decide, oh, I want to run some subroutine. I'd like to print something on the screen. Printf. Well, in order for that to happen, your code calls printf, a subroutine. It kind of needs a bookmark so that it calls printf, does what it wants, and now when that's finished, how does it know where to go back to? That bookmark is put on the stack. That's an extremely important thing, and why we're doing stack overflows, because that is going to be effectively the instruction pointer for us. It's called the return instruction pointer, but it ends up going into the part of the computer's memory that keeps track of where code is currently executing. That means we might be able to control where the code will go next. We've got some pictures to help you with this, and they are helpful to a degree. For me, anytime you look at a picture that tries to illustrate how they work, they're confusing to me. I'll show you why, and I'll explain why we draw the pictures the way we do. I want you to notice how it draws it here. First of all, it says, it has a little arrow. It says the stack is growing this way. It looks like it's going up, doesn't it? And it says memory addresses are going that way. What you usually see on these diagrams, I've excluded them here, you would see a little thing down here that says bottom of memory, and another one over here that says top of memory. And already we're going to be confused, because in the picture, where's the top? The picture's at the top, and we're saying that's the bottom, and the bottom says, why don't we flip it over? It's confusing no matter what you do. I'll explain why the pictures are always drawn this way. When a program begins running and memory is allocated for it, the stack is always going to point to the very highest memory address that that code is able to use. And as it wants to push things onto the stack, what will actually happen is it will take a little pointer, it's pointing at the top, it knows where it ends, and it's going to move it down a spot and push on whatever it needs. How does it know where the stack ends? It's the top of memory from the point of view of this application. The reason we draw the picture this way is that when you dump out memory, it does not start with the high addresses and work toward the low ones. When you dump memory out using any tool, it will always show you the lower memory here and the higher memory going down. That's the reason the pictures are drawn this way. Well, let's see what we've got on the stack here. In this case, we're looking at an instance where a parent routine is going to call a subroutine. So you can see down here at the top of the stack, we have what's called the parent routine stack. What's in it? I have no idea. I don't care. It really doesn't matter for us, and it doesn't matter to exploit this. I just know there's other stuff up there from the parent routine. The next thing on the stack would be the return address. That's where this is going to go back to begin or continue execution when the subroutine ends. And then the saved frame pointer. I already told you what that is. That's actually a pointer that says, hey, after you're done, move the stack pointer back over here so I know where my stack is, so it can find its data again. After that, we have any locally defined variables. Like here, we've got some kind of a pointer that's going to be able to point to character data. And we also have a local buffer called C. And then we have the rest of the unallocated stack space going down toward the bottom of the memory of the application. This unallocated space will go all the way down to the top of the thing called the heap. Not important for us, but just so you can orient yourself. That's where the heap would be. Well, in this case here, what would happen if in that function, in that subroutine, we were to store some stuff into the buffer called C? Well, if we store a reasonable amount of data, for instance here we can see that it's got space for 12. If we store a reasonable amount of stuff, everything's fine. It stores all of these bytes here, and nothing else is corrupted. Everything is fine. But as it's adding data, it's heading toward higher memory locations. This is the starting point for where the buffer is. And as data gets added, well, it goes down toward the bottom. I think you can see what we're headed for, right? What happens if we put more than 12 bytes of data in there? Oh yeah, we're headed for that next variable down. We're headed for trouble, right? by the way, let me just mention something that's a really common programming error. It's called an off by one error. Have you ever heard that? Off by one. And maybe you've wondered, what exactly does that mean? It means that the programmer stored some stuff in memory and failed to take something into account. For example, this buffer here, C, has space for 12 bytes. Programmers can make a very simple error and think to themselves, oh, I've got room for 12 bytes. All right, well, I've got 12 characters I want to put there. So they'll use a function like string copy, or they'll use something like string printf, or some function to read some data in there and copy those 12 bytes in. It's only 12 bytes long, right? And they fail to remember that when you copy in character data, most programming languages will add a null termination byte. They're called null terminated byte strings. What's just happened? Well, I only copied in 12 characters, and then it added a 0 to the end. Where does that go? It overwrites this byte here in the next thing up. That's an off by one error. I've accidentally overwritten some memory location. Those can be rather serious. They may not be serious. It just depends on the situation. They're always bad, though, because clearly we're overwriting data that we have no business touching. Let's see what happens, though, when we put in too much data. Now, we've kept the color coding the same, but in this case, we've put in a whole bunch of letters, and at this point, we've overwritten, well, not just that pointer. We've now overwritten the stored frame pointer, where the stack is supposed to go to, and then, now I didn't overwrite it with capital letters, but we overwrote the instruction pointer, the return pointer. The reason that this type of technique is necessary, to overwrite a memory location and then have that pushed into the instruction pointer, is that within the microprocessors that we use today, it is generally impossible to say, I would like to move this value into the instruction pointer. That register is the only one that we cannot move immediate data, an actual raw value, directly into the register. It's illegal. We have to put it somewhere else in memory first, and then we can get it into that pointer. Well, if the program is going to look at this value and move it into the instruction pointer for us, well, why don't we just put our instruction pointer there? So we've stored a value here, 0835C080. We're going to assume that's some memory location where hopefully we control some code. How does that code get there? What does it look like? We're going to talk about that in a little while. After we find a vulnerability, we'll look at what some shellcode would look like. There is something important I want you to note about this code, though. There are two main different types of processors that we use today. There are many things that can differentiate them. But in terms of how they store data, there are two primary types. We have what are called little endian and big endian. Because of how Intel processors work, which is by far the most common processor you'll run into, it's more efficient for them to store things in what's called little endian notation. That sounds like a really complicated concept, but we're going to make it very easy. The actual memory location we'd like to store things in is listed over here. It's actually 80C03508. If you look at what we put into the buffer, though, well, that's not what's in the buffer. What did we do in the buffer? The bytes are put in opposite order. In other words, we put the smallest byte, the littlest end, in first. So you go from the little end to the big end. That's little endian notation. Most other processors you'll ever see are big endian notation. That's actually simpler because it just means the number that's written here would be put into the memory exactly the same way. You put the big end in first. It's an easy way to remember it. Well, so far we've seen this is, in theory, how these buffer overflows could work. Let's see how we can find one, and let's see how we can write some shellcode for it. Heap overflows are going to be are also easy to exploit, but it's going to require that we take over some other region of memory. It requires a little bit more knowledge than these do, so we're not going to deal with them tonight. But they are not hard to deal with, and in fact, it's an area of very active research because there are a lot of protections that we've tried to put in place for stack overflows, and they're quite common. But heap overflows have fewer protections. Stack overflows were so easy that attackers never bothered with heap overflows until we started adding protections into our stacks. For the example we're going to look at tonight, I've disabled all of the different protections that we've added to our stacks these days. There are several. There are adding canary values. Looking at our picture here, that would mean we'd add some additional value here, and if that value changes, it's going to know we've messed around with the stack. There is something called address-based randomization. That means that all of the memory addresses are going to change every time we run the code. There's a bunch of different things that we're doing to prevent stack manipulation. I'm not going to get into it here. It's not the place. However, I will tell you that for every major strategy for protecting against stack overflows, not only are there papers written explaining how to do it, there are demonstration exploits and many exploits leveraging those techniques. So even though we have protections, every single one of them can be defeated. And it's well known how to do it. Let's talk about how we could find flaws, and then we'll turn this into something that actually works. To find flaws, the simplest way to go about it is this technique called fuzzing. It means that we're going to take some data and we're going to jam it into openings that we can find in an application. Now, quite often when you see demonstrations like this, you'll see the demonstration using some command line tool. In other words, we've got an application that runs on the command line and I can jam stuff into it. For our exploit, I wanted to make it something a little more realistic, something that would be more practical for an attacker. So we're going to take a look at a network-based application, and we're going to try to jam stuff into that and see if we can get a remote exploit to work. Because for an attacker, that's much more interesting than something I can run on the command line. To do that, I'd have to get on the box to begin with. A remote exploit is how you can get on the box. For our example, I've got a very, very simple network server. It's going to be listening on port 7777. It's going to accept some input. And of course, it's got a flaw. Let's just show you the code real quick. Let me find it here. It's around here somewhere. All righty. So up in this window, I'm going to run the server. And if you're interested in the source code for this, I've had some people ask. I've actually got a YouTube video out there that shows this whole demonstration. I've had people write in and say, hey, can I get the code? Because I want to try that. I want to try to recreate what you're doing. Yes, you can get the code. I'll put a link up at the end to a blog entry where we've got the source code. But I'm just going to run the server. We do not need to do any source code analysis to exploit this thing. That's one of our points. It's why we don't even look at the code any time in the demonstration. I'll get it running. I'll come back over here, and I'm going to connect to this. You could use Telnet, but I prefer to use Netcat because it's a little bit cleaner in its network connection. So with that running, I'm just going to connect to the local machine on port 7777. It connects. It says, hey, give me a command. You can see in the other window it's accepted a connection. We give it some information, press enter, and it shoots it back at us. This is not a complicated application by any means. But it is typical of a network server. It's a multi-threaded server waiting in the background, accepting as many connections as you'd like to send. Well, we said in our slide that what we need to do is send some junk. So like I said, I'm going to flip back and forth here. We want to create some unexpected behavior. How could we do that? What we want to do is send unexpected input. That could be that we send the wrong kind of data. Maybe we send data that's too big, too small. We send empty data. For most buffer overflows, though, you're going to be looking at too much data in too small a space. That's what an overflow is, right? There are some exceptions to that. There are some special conditions when you deal with integer overflows. But we're not going to get into the special cases. We'll just deal with the general case here. Well, in the slides, it talks about how we could go about doing this. It says what we could do is run the code in a debugger, watch it in the debugger, run an exploit against it, or send too much data and see if it breaks. I picked this particular example too, or this application, because in this special case, that won't work well. Let me show you what I'm talking about. I'll just clear the screen. I've got a debugger on here. It's very commonly used for this type of development. It's called GNU brand debugger. I'm going to execute my server with GDB. So when I run those two together, it loads it in, and now it's waiting to see what I want to do. I'd just like to run the server. Off it goes, waiting for connections. Now, I could take Netcat and send data to it. Now I said we want to stick too much stuff in there. How much is too much? I have no idea. So here's what I'm going to do. I'm going to take Perl, and on the command line you can actually send commands to Perl. I'd like it to run a very simple Perl script. I'd like it to print capital A. How about we do it 15,000 times into that network server? Now I'm just guessing here. I have no idea if that'll work or not. I'm just saying, hey, it asked for a small command. Let me send a lot of stuff. I could make that 150,000. I could make it 1.5 million. Doesn't matter. You pick a big number. Send it in. Oops. And I forgot, of course, to terminate my strings there. Hang on. Off it goes. Now there's a sign here that I have been successful. You may not catch what the sign is right away. So I'll point it out to you. Oh, actually, you should. It's still on the screen. When I ran this myself and I sent in some text right here, what did it do? It echoed it back to me. Here, it asked for some stuff. Well, it should have been sent there, and then it would send a received command with the echoed text. Do we see any of that? None of that came back. That's a very bad sign for the service. That probably means the service crashed. What's interesting is, if we take a look in our debugger, has the service crashed? Is it still running? In fact, let me come over here. Let's connect to it with Netcat again. Is it still running? It's still running. But I know it didn't respond correctly. What happened? This is a multi-threaded server. When you attach a debugger to this thing and run it, every time it spawns a thread, that's a separate process. For me to capture that crash, I would have to, while it's connecting and before the exploit comes, connect another debugger to that thread. And is that getting complicated? There's a way easier way to deal with this. It says it at the bottom. Turn on core dumps. Core dumps are disabled by default on most Unix systems today. I've turned them on this one. It's very easy to do. You just type ulimit -c for cores, no limit. When you type that command, it is now able to create core dumps. So let me stop the debugger back here, because that's not helping me. I'll clear that out, and I'll just start the server again. I'll come back over here, and I'm going to run the same netcat with 15,000 characters. I get the same result, except that now, notice I have a file called core. So at this point, I've managed to get the application to crash, and it has created a core dump. It says at the bottom here I should open that up in the debugger. Why? Well, when I open that up in the debugger, it's actually going to, I'm sorry, let me just get to my screenshots in the right place. So this was demonstrating what we just talked about. Here we've got the core has been created, and now we're going to open it up in the debugger. When I open this up in the debugger, let me do it up in this window so it's nice and big. I just run gdb and tell it, hey, I've got a core file. When I open it up, it's not going to try to run the program. A core file, a core dump, is an image of the memory of that process at the point it died. It just dumps the whole thing to the disk. GDB now has read that into memory and has put everything back where it was at the point that things died. So it's sort of like a snapshot of where we crashed. Notice down here that it's telling me that the problem where it terminated, it says terminated with signal 11, segmentation fault. That means we tried to read or access memory that does not belong to our process. And it tells me down here, here's where it tried to do it. 0x4141414141. Now you may not know this, but the letter A, the capital letter A, in hexadecimal, I see you nodding, it's 41, hexadecimal 41. What does that mean? That means that our program tried to load a whole bunch of capital A's into the instruction pointer, and then the program said, hey, where are you going? You're not allowed to access that memory. How can I see what those registers look like? How can I prove that's the case? Well, it's not going to be a debugger class or anything, but let me just show you what the registers look like right now. Currently, the registers contain a number of useful values. For instance, here I can see where the stack pointer is. I can see over here. Now this is interesting. the EBP is currently also all capital A's. That's because this is usually going to be used as we're returning to get to the original stored frame pointer. I've overwritten that value as well. But further down, notice the EIP. That's the instruction pointer. So it actually did read that value off the stack, move it into the instruction pointer, and crashed. Excellent. At this point, we have already demonstrated that this application has a vulnerability. If you can get to that point, you've done enough testing to know you've got some code problems. But how do we take it to the next level? How do we actually exploit that? Well, let's talk about that a little bit. What we know so far is we've had a stack overflow. I know because of how it went about happening. It's overflowed a piece of the stack. In fact, as additional proof, I'm going to use a display command, it's the X command, to display 64 bytes of memory beginning at the stack pointer. The stack pointer is currently here. So I'll just type that value in. It's at BFFFECE0. Notice what all of the values are that you can see on the screen. Clearly, this is a stack overflow because the stack is crammed full of capital A's. All right, so with that in mind, we know that we've got a successful overflow. We know that we've got an override of the return pointer. Now what we need to know is how big is the buffer and where is it? Let's see what we can do to find that out. If I were doing this for exploit development, I would probably do another thing along the way here. Let me just show you what that is. I've removed the core file. I'm going to restart the server. And I would go back and retry that same exploit, stop it again, and reload the core file. And the reason I would do it is to see whether or not the values on the stack are changing. Now, I do actually see an interesting change here. I see I went from EC to ED. At least I think I did. Was that an ED before or an EC? I don't remember. But you know what? I think it might have changed. Let me quit that again. And this is why you would go through this process. We're looking to see what stays stable. Get the core out of there. We'll restart the server over here. And we'll run this one more time. Take another look at the core file. ED0. Oh, no, ED30. No, it seems to be staying the same. Maybe I just missaw it the first time. So my stack seems to be pretty stable. The stack pointer doesn't move. I'm still overriding the instruction pointer. I'm still overriding the EBP. Great. I need to now figure out how big this buffer is. I need to know where it starts, and I need to know where it ends. How many bytes does it take to overwrite the instruction pointer? The traditional way of doing this is to repeatedly run the exploit or the attack either with a debugger attached, which we've already said in this case is going to be a pain in the neck. So instead, we're going to repeatedly have to run it and analyze core files to figure out where the buffer starts and how many bytes it takes until we get to the instruction pointer, and then count. Does that sound like fun? There's a way easier way to do it. And we're going to start leveraging a little bit of what Metasploit has. In Metasploit, there's a lot of stuff that comes with it. This is just the command line interface to where stuff is. There's a tools directory that has some fantastically useful stuff for exploit development. Makes your life really easy. For instance, there is something here called pattern create. Instead of me counting how many letters there are, running it a lot of times and figuring it out, here's what I can do. I can simply run pattern create. And if you just run it with nothing, it'll tell you, here's what you need to do to make that happen. OK, we're going to use just the default option here. I'm going to say, give me, I'll just say 2,000 characters. Press enter. And what it generates is a pattern of characters that I can take and plug in to send into that buffer, and then look at the result to discover how many bytes it takes. Instead of me talking about it, let me show you what I'm talking about. I've already used pattern create to create a file over on the other machine. Let me restart the server, go back into the over here, and I've got this little file that says 2K pattern. It's just that pattern out of Metasploit, OK? So there's nothing special in there. I'm now going to take and I'm going to cat that through Netcat to that service. After I do that, we'll come back in. We'll take a look at what that core file looks like now. And, oh, you know what? I didn't remove the old core file. Let's try that again. All righty. Notice that the value it returns here is different. It's no longer 414141. If we look at the registers, I can see that that value is actually stored in the instruction pointer. It's taken that pattern and pushed it into the buffer, right? Now, I can take that value and use a second tool that comes with Metasploit. The second tool is this one here called pattern offset. So if I simply run pattern offset, again, I won't give it options so we can see what it needs. It'll tell me what I need to do is tell it what to search for and what the length of the original buffer was. In other words, how big was the pattern. So I'll run it one more time, and this time I'll give it the value that's showing up in the EIP, 65413165. Can you guys help me with that? OK. So it was 0x65413165. Is that right? Maybe we double check that. Yep, that looks right. OK. And it was, how big was the buffer? How big was the pattern we sent? 2,000. Oh, that's 124. Let me tell you, this saves you hours of time of playing and counting and moving. And 124, there you go. That's how big the buffer is. In other words, that's how much distance there is from the start of whatever it is we're overflowing to where the instruction pointer is on the stack. Is there other stuff in between? I got no idea. Frankly, I don't care. I just know that that's how big the buffer is. All right, let's come back over here, catch up with our slides. So we found the pattern. There it is. Now we can calculate the offset. We know it's 124 bytes to work with. Now we know how much space we have to work with. We also know what the stack pointer currently is. That's useful for us because it tells us where the stack is, and we might be able to use that to replace the instruction pointer. So if we could get some code, put it on the stack, right at that location, and then replace the instruction pointer with that stack value, we could just jump right into our code. To make that happen, we're going to need some code, right? All right, let's see what we can do for some code. To get some code, we've already talked about this, some additional things we can find. Let's talk about writing the shellcode. At this point in time, we figured out how big the buffer is, how much space we have to work with. We would also have a feel for whether or not there are any stack protections. Is there address randomization? Is there a canary? We don't have any of those in this case, so we don't have to worry about them. And we also have a pretty big buffer, 124 bytes. Doesn't sound like a lot, but that's plenty of room for an exploit. With that much room, it probably makes sense for me to write some shellcode. That's what we're going to do. What if I had a really small buffer, or maybe there was address randomization, or, well, in those cases, I would start looking at discovering where existing functions are, maybe shared libraries that are already loaded, because they will always be at the same address. Knowing that, I could return directly into one of those. All I would have to do is put the correct arguments for that function onto the stack. I'm controlling the stack, so I can do that. And it may only require maybe 10 to 15 bytes of data, a really small buffer. For us, we're going to stick with writing the shellcode. To create some shellcode, and what I just described, by the way, is either called arc injection, we're changing the program arc, or a return to libc attack. That's when we return to existing code. We're not adding our own. We're instead going to write our own shellcode. Writing shellcode, there are some suggestions that, well, what you could do is you could write it in C first, and then you compile the C to assembler, and then take the assembler over. But almost always, the assembler that's going to be created by your C compiler is not going to be particularly useful as shellcode. There are certain things that it's just a bad idea to try to send in shellcode. For example, very often buffer overflows are occurring with strings. And strings, we already said, are called null-terminated byte strings. What does that mean? What happens when you hit a null in a string? you stop processing the string. So if I end up with any nulls in the resulting assembler, it's just flat out not going to work. For that reason, it really is better to write it by hand. So we're not going to actually sit and write it. I've got some shellcode I've written. I'm using it as an example because you really can go out and download oodles of shellcode. For instance, if you go to millworm.com, there's an entire shellcode section, and there's a whole bunch of shellcode for any processor and operating system you're going to find. Metasploit also has a whole pile of shellcode in it too. So you often don't have to write your own, but we're going to take a look at a quick example here. What this shellcode is going to do is execute the /bin/sh command. What's that going to give me? A shell. Hey, that's perfect. That's what I'm looking for. So here's what we've got going on in the code. First, our first command here is going to move some value into EAX. Now, I've put over here in the comment that it's moving in a /sh. That's actually not really what it's moving in. What's really getting moved into EAX here is HS/2. Now, I'll explain the /2 in a second, but it's moving in HS/. That doesn't look like /sh, does it? In fact, it's backwards. The reason it's backwards is that when I call execve and it goes to read this string, don't think little Indian. That's not the answer. When it goes to read this string, it's going to suck it off the stack one byte at a time and reassemble it. So that means that I need to put the characters onto the stack backwards. But what about the 2? Well, remember we said that we have to avoid null characters. It doesn't have to be a 2. I could actually use absolutely any value there except a null. Because look what I do right after this. I move this value into EAX, and the very next thing I do, anyone know what that instruction is? Shift right. It's going to take the bytes that are sitting in EAX, and it's going to shift them over 8 bits. So that little 2 that's sitting over here on the right-hand side, HS/2, what are we doing with it? We are shoving it out of the register. And guess what gets pulled in on the left-hand side of the register? Well, so the HS/ moves over, and what ends up on their far left-hand side? So we shift the 2 off, and what comes in on the other side? A null. Remember, I can't send a null, but I just created a null in my code. So I've now added the null onto the end of the sh. So it's now null terminated. Now I stick that on the stack, because that's where it needs to be when I run my function call. Next thing I do is I push on/bin. It's actually nib/, same reason, and move the, here it is, and push that on the stack. So now on the stack, we have the /bin/sh with a null. Perfect. I now move the stack pointer into EBX, because on the stack, what I need to have is a pointer to where the string is. That's going to be the pointer. That's currently where the stack is. And I also need a 0, because I'm going to need to have a 0 on the stack as well. It's part of what execve needs. Well, I can't move a 0 anywhere, but I can do this. This is an exclusive OR. When you take a value and you run an exclusive OR against itself, you get a big fat 0. Are there other ways to do that? Yeah. Couldn't I do a shift right 32 bits? Couldn't I do a shift left 32 bits? Couldn't I do a sub EDX, EDX? I mean, there's lots of ways to do it. We just used an XOR. Yeah, that's exactly what it is. It's the null that I need to get there. And now I'm going to push this stuff onto the stack. I put the null that I need for execve, and then I push the pointer to where the string is that I need to execute. Next, I move the ESP into ECX. That is the pointer to where the arguments are supposed to be on the stack for the function call. And finally, I put a 0 into EAX, and then move a hex B, that's an 11, into AL. Why the heck do I do that? Why wouldn't I just move 0x0b into EAX? Well, it turns out that when this actually gets assembled, when it's turned into machine language, some of our operands are bigger than others. If I do a move of this 1 byte value into the 32-bit register, when that gets compiled into machine language, it turns into a 32-bit immediate value. The immediate value is 0,0,0,0,0,0,0,0,B. Is that a problem? Yeah, we got 3 nulls all together there, right? So instead, we just move the 0 we already have into EAX. EAX is now empty. And now I replace the lowest part of that with the 11. That allows us to move a single byte value into a single byte register. No nulls. And finally, we call interrupt hex 80. That's the system call on Linux systems, which happens to be our target here. In other words, we've now got shellcode that can run execve with /bin/sh. What do I do next? I need to compile it. Easy to do. I do see people go out and they go and get themselves an assembler. Like there's NASM. I mean, there's a lot of assemblers out there. And you can help yourself. But you know what else you can do? You see it here on the slide. You can just use GCC. You probably already have that installed. So I come back on over here. Let me kind of clean up where I am. All righty. And I'm just going to run. I've got that shellcode, by the way, just sitting there in a file. It does have a few pieces on the top of it. This is just stuff that has to be there to get it to compile. So I've just added a little bit, but the rest is everything we talked about on the slide. And all I have to do is run GCC. I'm adding a -C option. Now, if I just run GCC against this file, it's going to compile it and link it. I don't want it linked. I just need the object code. I need the machine language. So I run GCC-C against the shellcode. And that will create for me a file called shellcode.o. Shellcode.o, well, you can't really cat it. I'll try. It's probably going to regret this. But I can't cat it. You can see that, oh, look, there's a bin.sh thing going on. There's the 2, right? So there's stuff in there that's kind of recognizable, but this is not useful for me. What I really need to do is get the binary part of it. There's some options. You could use something like hex dump. This is not probably a great option, but you could use hex dump and then find your code. I happen to know my code starts right here and goes to right here, but that's not useful for most people. You know, I happen to know that, but how would you know? There's a much easier way. There's a really handy tool called objdump-d for dumping out object code. And look what it does for us. It says, oh, here's your assembler instruction, and here's the machine language to make it happen. All I need to do is copy these bytes in order into a file. Now, it can't be ASCII B832. It has to be the binary values. There's a super easy way to do it. What we're going to use is Perl. We're going to use Perl again. I'll say I'd like to print, and now I just have to list out the hexadecimal values, but marking them as hexadecimal. In Perl, very easy, a \x in front of each value. So I'll just do it in order. Please watch me and make sure I don't get any wrong, because if I get them wrong, of course the exploit won't work. So we got B832-2F73. Oh, thank you. I forgot the X's. Thank you. 73, 68, C1, E8. Oh, E8. Thank you very much. 0850 68 2F. What? Did I miss one? I'm good. 62696E. This is probably the most tedious part of the whole exploit, okay? Sorry. We only have to do it once, don't worry. I'll give you a tip after I finish this. 89E3. D252 5389 E1. Almost there. 89. D0 B0 0B CD 80. Whew. How many times do you want to type that? Now, I see people teach this stuff, and what they do is they say, you take that and you print it through Netcat, and that's a big mistake. Because you know what? I went to the effort to write the shellcode, but the chances that this exploit is going to work the very first time, they're pretty darn slim. So instead, let me just take that and stick it in a file. How's that sound? There's two great benefits to that. One is I can reuse it as many times as I need. The other one is one of the very next things I need to know is how big my shellcode is. Now, you could go and count the bytes, but guess what? It'll tell you it's 28 bytes. See, isn't that easy? So stick it in a file first. Let me just catch up over here. So shellcode is bytes. We copy the bytes in, stick them in a file, and we know we have 28 bytes of code. Great. We've now got shellcode. We've got some information about the vulnerable application. How do we turn that into a proof of concept and see if this actually works? It's actually very easy. We have everything we need so far. We have knowledge of the flaw. We've got shellcode ready to go. We need to figure out how to get it on the stack and set the return pointer appropriately. So we could use maybe Perl to put this all together for a proof of concept. And if I'm doing exploit development, that's the way I'm going to do it. We could also try to turn this into an executable file and bundle the whole thing together. That's generally a waste of time. It's easier to just do it as a proof of concept and then port it into Metasploit. What you're going to find is that once you know a little bit about Metasploit, converting this exploit and all the time we put into it into something on Metasploit takes less than 2 minutes. It's actually extremely fast. So let's see how we can go about launching this thing in. We know we have a 124-byte buffer. We know that the ESP is pointing to this memory location, and I have a 28-byte shellcode, which means I've used up 28 out of 124. There's 96 more bytes that have to be filled in. What can I fill in those extra bytes with? You can actually fill them in with any single byte instruction that is not going to mess you up. For instance, a return would be a bad single byte instruction to use. But if you can come up with any single byte instruction for the platform you're on that will not have a negative effect on how your shellcode executes when it gets there, go for it. For us tonight, we're going to keep it super easy, and we're going to use no operation. We're going to use NOP. The reason for using a single byte instruction is we may not be able to land exactly where our code is. As long as we land somewhere before it, and those 96 bytes before it, we'll be able to slide right into where our code is. That's what a NOP sled does. How do I make that happen? Well, let me come on back over here. I've now got the shellcode sitting in a file ready to go. I know that I want to have a 96-byte pad in there of some kind. We decided we were going to use NOPs. So again, I'll just use Perl. I'm going to print out hex 90. That's a NOP. 96 times. Well, that's easy enough. I'm going to send that into a file called, how about NOPs? That good? Just make sure it's the right size. Yep, 96 bytes. I check on that stuff because I miss things sometimes. And if you leave off the \x, for instance, you're going to have a different value there. So I can see immediately I made a mistake. Next, I need to get the memory address somewhere. Well, that's easy too. Let's use Perl again. Let's do Perl-E print. Now I need that memory address. Let's start by using the, let me go back a slide here. Let me start by using the ESP. Now I'm going to tell you, this probably won't work the first time because I know where the instruction pointer is, I know how big the buffer is, but I really don't know what else might be changing on the stack between the time my buffer gets filled and the time this thing returns from the subroutine. So that means if something else between me and the return pointer changes, I may not know it until I try to run my exploit. So it may not succeed immediately, but it's a starting point. So let's use that value there, the 0xbffed30. When I print that out, I need to print it backwards. Remember, I have to put the little end in first. So 30 ed ff bf. Does that look right? Ed, sorry. Ed ffbf. Looks right. We'll see what happens. And I'm going to stick that into a file called address because I like to be organized. Now that I've got all those pieces there, I'm going to come back over here and start up my server. And you know what else I ought to do? I should probably remove the core file. And then I'm going to just cat all of these things together. I'm going to cat my NOPs, followed by my shellcode, followed by my address, through netcat. Now cat is just going to take that first thing, off it goes, and it just piles them together. There's nothing else between them. It sends the raw data. I don't need any other tools. 127.001.7777. Press enter. And, well, it ran. It did something, but I don't see a command prompt anywhere. OK. Now, there's two things I'm going to do. The first thing I'm going to do is so I don't forget. When you try to run an exploit against something and it fails, even when it succeeds, chances are you've corrupted some memory structures over there. So I'm just going to come over here and stop the server and restart it so that when I try it again after I make some changes, the memory is not corrupted. Because if it is corrupted, my exploit may actually be functional, but will fail to work because memory is no longer in any expected state. Do I what? I am going to use the core file right now. I want to see what's in it because I thought I should be kind of in the right place here. Let's see what happened. So, oh, well, that's interesting. Program illegal instruction, 0xbf. I'm really close, but something went wrong here. I look at my registers. Yeah, that's what's in the instruction pointer. That is where ESP is. Something's odd there. What I could do is I could dump out what the stack looks like at this point. So I could dump out BF, FF, E0, D30, and I see that. Oh. Now I pushed 90s in here. I pushed in NOPs, but look at this. There's other stuff going on here. What's happening? Here's what's happening. My buffer overflow did not immediately crash the code. And it went on and completed whatever that function was doing, and now the stack is in a different condition. But look what else we see. Look at location 50. Look what's there. Those are my NOPs, right? So if I simply move my instruction pointer forward 16 bytes, remember this is all in hexadecimal, right? So it's 120, I'm moving it. 16 bytes, we should be groovy, right? Let's give it a try. What? I think I meant 16 because it was, oh no, 32 bytes. 32 bytes, 16 bytes? How much did it change? Yeah, 32 bytes. 32. I already removed the core. It was 32, right? OK, 32 bytes. So let me come back in here and let me find where I printed my address. There it is. All I need to do is change that to a 50. And now everything else is already there, right? I don't have to go edit files, or that's why I like to stack them together that way. Oh, what's going on in the back window there? It spawned a shell. Now, in this particular proof of concept, I don't need to go any further. In this particular case, I actually cannot command it from over here. It didn't return the shell to me, but it did spawn the shell. It's back over there. But I just needed the proof of concept. I needed to get the memory addresses, figure out how big things were. Now that I have that, I'm actually ready to move this into Metasploit. Let's see how we do that. Let me again catch up with my slides. Launch the exploit. There it goes. Convert to Metasploit. Let me get this ready to go too. There we go. Start the server again. And also, let me just get its IP address. ifconfig. And I'll just keep that on the screen. I'm going to need that to run the remote exploit. So I have a working proof of concept. What do I need to turn it into Metasploit? A basic, very, very basic Ruby knowledge is useful, but not required. What we look at is a Metasploit exploit. And we can kind of look at this Ruby file as a template. Now, this is the hardest part of using Metasploit. But after we show you just a couple of things about it, it's actually very, very easy. You take any existing exploit that uses the same kind of service you've got. I have a TCP service, so that's the kind of exploit I would go and find. And I'll just open it up in an editor and get started making some changes to it. Let me get this out of the way. And somewhere here, oh, I think it's actually down here. Somewhere down here, I've got a file I've already written that has the exploit in it. And we're just going to talk about what's in it. There is, unfortunately, some secret sauce in Metasploit, and I don't particularly care for that, but that's just the way it is. So All of this stuff you can just inherit out of the skeleton file, out of whatever exploit you started with, and you chop out anything that made it specific to that service. For instance, it will always have require MSF core on the top. You just have to know it has to have that. Start with a sample file. The next part, class Metasploit 3, MSF, exploit remote. Again, I took this from a kind of service that's like mine, a TCP service. So it's already there. I don't have to mess with that. And the same goes for here. These are pieces of the Metasploit framework that you kind of just have to know exist, which is what makes it hard to use. The easier thing is to start with a template and just fill in the blanks. So I leave all that alone, and I don't have to start changing things until I get down here. I really don't even have to change these, but it's a good idea to. We have a little mapping here that describes parts of the exploit. And you don't have to know Ruby for this. I can see, oh, name. I'll bet that's where I put the name. Let's call it course example. And then the description. Oh, OK. The description is going to go in there. The author, the revision, the payload. Now, inside of the payload, we need to tell it how much space it's got to work with. I actually moved this down to 108. I did a little testing earlier today, and I worked out that I can actually get away with 16 bytes, accounting for an additional 16 bytes instead of the 32. So I've already done that calculation. And I moved it from 124 down to 108. This actually makes it much, much more reliable. If I use the 124 here, it's going to be an unreliable exploit. It will work sometimes, but not always. Just moving it that 16 bytes made a big difference. If I moved it to 32, it'd probably be even more reliable. But I want to keep as much buffer space available as possible, so Metasploit can use a wider range of payloads. I say it's got 108 bytes. I can specify any bad characters. In this case, we actually do have one. We have the null character, but I'm not even going to bother putting that in here. And I can specify any default options. And for those of you who have seen Metasploit in the past, you're probably starting to see some familiar things, like our port. Where is the remote service? Now, I could make the person using the exploit figure that out, but it's defaulting to 7777. So I'll just set that. And then you define any kinds of targets you've got. Well, this is a Linux exploit that works on Linux platforms. And why there's a familiar value, that was the return address we came up with. In reality, the only things I really need to put in here so far, are probably the port number, definitely the space, and the return address. That's really all I have to put so far. Then down at the bottom, we can skip down to where the actual exploit happens. This is the only other piece I need to change. There will probably already be a payload in there that does something from where you copied it from. You can just take that all out, and here's what we put inside. We tell it to, first of all, connect to the remote site. We then start building a buffer. What I'd like to put in the buffer is a bunch of nops, and I'm going to put in 16 nops. Remember I said that I moved it off by 16 bytes? We did it 32 in our proof of concept, but I discovered that 16 worked too. So I'm just padding this out by 16 bytes, because the buffer is 108. I need to account for the other 16 to get to us to 124. So there's the 16. And then I tell Metasploit, hey, take whatever payload the person has asked for and encode that and put it onto the end of the buffer. Great. Do I have to tell it 108 bytes? That's one of the great things about Metasploit. I don't have to be specific here. It now says, oh, let's see, I got 108 bytes to work with. All right. With 108 bytes, here are the payloads that are possible for you. Pick one. You pick one. It takes care of packing that up. It adds whatever padding it needs and sticks it into the payload for you. It's out of my control. I don't really have to write shellcode. I could write a single piece of shellcode for all my proof of concepts, and the only thing that changes is the return address, because Metasploit will take care of all the payloads for me. Finally, I tell it to take the address and pack that into a binary little endian value. This is kind of the magic that makes that happen, and add it to the buffer. And then send it to the client and hand it off to the handler. So in all, we had to set 3 values and do a little bit of stuff here, which is fill in the blank kind of stuff. Once that's written, I can come back over here. And oh, by the way, I'm sorry. Where you put that turns out to be pretty important. What you would then do is go into the Metasploit directory, into the modules directory, into the exploit subdirectory, into the Linux subdirectory, and I've put it into private sbs.rb. So that's where my exploit will be found. Now I'm ready to actually try to run Metasploit and see if this thing works. Okay, I get a Ruby error because I'm running on a Mac. It's just the way it is. Give it a couple seconds. It's got to load up all the exploits and all that stuff. It's now ready to go. I tell it, just like you would in a normal Metasploit exploit, I would like to use the exploit called Linux private, oh, there it is, SBS. I would also like to use a payload for this. I want to get it to do something. So let's set the payload to be, let's see, how about it's going to be some kind of Linux x86 thing. That sounds good. I'm looking for a shell. Okay. These are the possible shells that can fit into the space I've told it about. I'd like to use a shell bind TCP. I just had it run a shell. I wanted to bind a shell and let me command it. There we go. I don't have to write anything. I don't have to change it. It does all that for me with the sizes I've given it. Let me take a look and is it info options here? No, that's not it. How do I see the options on this? I forgot. Show options? Too many different tools, right? So I see that I have some things I need to fill in. The only thing I need to fill in, I need to tell it where the target is. Well, where's the target? That's what this IP address is for. 192.168.145.131. So let's set our host to 192.168.145.131. Is that right? Yep, looks good. All done. And what's the magic word? Exploit. Off it goes. Oh, it says command shell has been opened. Hey, look what's happened. Oh my goodness, it took us 60 minutes. 60 minutes from finding a flaw and explaining it all the way along the way, and we've now got a working exploit that will work with any payload that can fit into that space. Now, I hope you found this interesting, right? I mean, we tried to make it simple, tried to make it interesting. It is really cool stuff. There's not more that we're going to talk about here. But if you are interested in this, if this is something that you need to do, if you're like, how many of you guys are in the hacker exploit class this week? 2 people, 3 people, 4 people, okay. If you're like, wow, yeah, okay, I need some more of that. I need to develop my own. There's a really awesome class that's taught by a guy named Steven Sims. It is by far the best exploit writing class I have ever seen. I'm not saying that because he works for SANS. I don't get any money out of it. It is really an absolutely awesome class. To take the class, you should be familiar with assembler. You should be comfortable looking at assembler. If you're not comfortable looking at assembler and running a debugger, that class is not for you. But in that class, he will take you step by step through how to defeat every memory and stack protection mechanism there is on all of the major platforms. So by the end of that class, you would, for instance, see that there's an alert, oh, there's a buffer overflow condition or a heap over or an off by 1 error in Adobe PDFs. And after taking this class, you can create your own exploit with no other information because they very often don't print much, right? Undisclosed, no further information. And be able to create any exploit for any platform. I mean, it's a fantastic class. It's definitely for advanced penetration testers. The other thing is, the problem we demonstrated here is just one of the many kinds of programming flaws that exist. There's another class we've got that's going to be released very soon. We've taught it before, we just rewrote it. The number actually changed. It's not 538 anymore. They've changed the number on me to 543. It is not an exploit class at all. We will explain briefly how exploits work, but what the class really is secure coding in C and C++. Because those are the primary languages that create almost all of the problems we face. One of the reasons is even if you're writing code in Ruby or something else, you know what language that was written in? C or C++. So it's the underpinning for most of the things we've got. So that class is an awesome place to send your developers so that you know that they know how to write secure code and prevent these types of problems and won't run into having Metasploit exploits run against you. So if you guys got any questions, feel free to ask. If you don't have any important